Hello and welcome back, and in this video we're going to look at the domain of a function. So we're going to be looking at different types of functions, and if there is a domain that is restricted, that means are there values that we cannot put into the function. So remember, the domain of a function is the input values, or sometimes we call them the independent variables. So in this case, when we're writing them in function notation, this right here is going to be our input value. This is a function of x, as x is its variable, and these are what we're going to do with the variable x. This is the rule that we're going to use to form the function values. So when we look at the inputs here, you should ask yourself, is there values I cannot put in for x? Is there something that's not going to be defined, or is there some value to this that I can't plug in and cube or subtract? And in this case, there aren't any restrictions on the domain. I should be able to put in all real numbers here. So all real numbers is the domain of this first example. Now there's several ways we can state all real numbers. We can just write it in words. We can use a symbol for all real numbers. This is capital R. Sometimes script R, that is it, or they use this one with two lines. This R means all real numbers, or they can use set notation. So sometimes we use set builder notation to talk about the domain. Set builder notation starts with set of all x's such that something occurs. So that's set builder notation. So sometimes we use set builder notation to describe the domain. So sometimes this is called set builder notation right here. And when we do this, this bar means the words such that. So all x's such that something occurs. And that's set builder notation. But the domain of a function is really just what values can we put in. So if you write this, all real numbers, if you write this script R or this one here, as long as you mean all real numbers here, I can put anything in here, cube it, subtract it, and add 1 to it, and I should get a value. Now in some functions there's going to be restrictions, so we may not be able to put in all the values. So if we're looking at this function, there is some restrictions to the domain. There are certain values that we cannot do. We cannot divide by 0 in a fraction. We cannot divide by 0. So that means there's a restriction here. There's this part of the function restricts the domain, the denominator. We can put anything we want up here for this x, but then this one we can put numbers in here, but there are certain numbers that are not going to occur. What we would want to do is we cannot divide by 0, so what we're going to say here is 2x minus 1 cannot equal, that's with the slash through it, cannot equal 0. And we're going to solve that. We're going to add 1, get 2x is not equal to 1, and we're going to divide, and we're going to say x is not equal to 1/2. So we're going to say everything works except for this number right here. Now if I write it in set builder notation, like I mentioned earlier, this would be all x's such that x is not equal to 1/2. So that would be the set builder notation for that problem. Or you can write it in words. You can say all real numbers except 1/2. Alright, if you wrote that in words. Okay, so a denominator gives you a restriction. The other type of function that gives you restriction is a square root. A square root gives you a restriction also, because we cannot take the square root of negative numbers and get real answers. Cannot take square root of negative numbers. And get real answers. So we want to make sure we have a real answer out of this. So what we would do to find the domain on this one is we would say, since we can't do negative numbers, we'd say that the square root, or the value in the square root, has to be greater than or equal to 0. So if we can solve this, this will give us our domain, because anything less than 0 is negative. So what we want to do is solve this problem, that's what's in the square root, is greater than or equal to 0. And if we do that, you should get x is greater than or equal to negative 5 divided by 3, negative 5/3. So writing it in set builder notation again would be a set of all x's such that x is greater than or equal to negative 5/3 is our domain for this problem. That means that if we use any number less than negative 5/3, we wouldn't be able to do the problem because we'd get the square root of a negative and we'd end up with imaginary numbers. So we could do it, but it would be imaginary, and we're looking for real numbers out of our system. So that's what we're going to be looking for in this part. In this part, we're looking for real answers. All right, this next example, we have both. We have both here. We have a square root and a denominator. So I've combined these two problems together, where we can't divide by 0 and we can't have negative numbers, into one problem with the square root in the denominator. So basically what we're saying here is I can't have this being 0, but it also can't be negative. So that means we're going to say, in this one, we're going to say x minus 1 has to be greater than 0. We can't include it. So it's going to be different than the one up above because we can't have an equal sign here. If we had an equal sign, then we'd have a 0, and we'd divide by 0, and it would be impossible. We wouldn't be able to do that problem. So in this one, solving is much easier than the one before. We just add 1 to both sides. We get x is greater than 1. So the answer to this one is x. All x's such that x is greater than 1 is our, oops, not equal to. I was just saying that it wasn't equal to. I wrote it down wrong. So just all x's greater than 1. Because if we wrote 1 in here, we'd get 0 and we'd have 1 over 0, which is not defined. So we have to say it's greater than this one. This one we can put in negative 5/3 because negative 5/3 would give us 0 in this, and the square root of 0 is 0, and that's possible. We just can't do it in this one because it's in the denominator as well. Alright, so on this one, the last example I have here is one where we have a denominator. So what we're going to be saying is that same thing as above, x squared minus 16 cannot equal 0. So that's the same as this example up here. What we used here, the denominator cannot equal 0. It's the same problem. But in this case, it's a square, so that means we need to factor it in order to get the solutions. There's actually more than one solution to this because we can factor it in this way. We have actually 2 exceptions to this. So in this one, x minus 4 cannot equal 0, or x plus 4 cannot equal 0. So in that case, there's two exceptions to this. X cannot equal 4, or X cannot equal -4. So both of those cases would not work, and if we plug those back in, we could see that. If I put 4 in here and square it, that's going to be 16 minus 16, which is 0. And if I put in -4, I also get 16 minus 16, which is 0. And both of those would be undefined. So this would be my domain. It would be all real numbers except these two values. Alright, so those are some examples of domain and how you would write it in set builder notation. You can also write it in words, or you could write it with inequalities, as long as you have some words and inequalities. I could write this as all real numbers except 4 and -4. If I wrote that in words, that would be okay. Alright, if you have any questions, send me an email.